When I start this emulator, there is no Windows, no Linux, not even a DOS. The BIOS runs instantly and I am playing Tetris. How does a PC go from power on to a game on in a second? Let's dive into the bot sector, see what the hardware is actually doing, and build an OS from scratch. When a PC power on, the CPU has no idea about files, graphic, or even a keyboard. It just jumps into a fixed address in memory where the BIOS lives. The BIOS checks the hardware and then it looks for a bootable device. If it finds a hard drive, it will read exactly 512 bytes from the very first sector. The first sector of the disk is a master bot record. Just 512 bytes to start your operating system, and at the very end there must be a magic signature, AA55. Without that, the BIOS refuses to boot your disk. If you want to be compatible with existing partitioning tool or dual boot with Windows or Linux, you need to add partition table. Partition table takes 4 times 16 bytes and reduces size of our bootable code. So my first change was to fit a bootloader into a half of a kilobyte. Bootloader is always loaded into the same linear memory address, 7C00. This is just hexadecimal number that can be converted to a decimal using this formula, where C in hex is just 12. When we write bootloader, we need to take that into account to correctly use memory. Bootloader will be written in assembly language, because it's easy to set memory offset to 7C00. This is important to correctly access variable in the code. Keep exactly 512 bytes. Keep magic AA55 at the very end. Create 16-bit code. PC bought our code into what we call a real mode. We choose segment offset addressing that can be converted into a linear address by simple calculation, which is segment times 16 plus offset. Yes, this way both segment offset address point to the same linear address. This code sets offset to 7C00, so all addressing in our code will have this shift. We also set code to use 16-bit version. Next we run XOR AX command on our AX register. This simply set AX to 0. Then we copy this value to all segment register. Because we are informing compiler to use 7C00 shift, we do not need to use register for shifting. Finally, we are setting stack address right above our bootloader. When we are putting something on stack, this address is subtracted by a size of a value that we put on a stack. This means we will never overwrite our bootloader. 512 bytes is not enough to do all initialization. We need to initialize hard drive, file system, graphic, keyboard, memory management. That's a lot for 512 bytes. So we need a way to remove this constraint. To do it, we will use our bootloader to only load our stage 2 loader that does not have size limit. This stage 2 loader will then initialize everything we need to start our operating system. We can use BIOS interrupt function to load data from HDD into memory. You can think about interrupt function like a simple function exposed to us by BIOS. Interrupt number is like library containing multiple functions, and the number that we set in AH register is a function ID in that library. Here's the example of function reading from the disk. We will use 13 hex interrupt and function with ID 42. We will pass all arguments using assembly registers. This image shows function input parameters. AH is a function number, DL is a driver index. We are using HDD, so we will set it to 80 hex. DSSI pair should point to a DAP structure, and this is a DAP definition. We define our DAP to load our second stage loader. Stage 2 sector is a size in sector of our second stage loader. Values provided during build. And stage 2 LBA is a linear sector number on a disk where stage 2 loader starts. We will load it into 8000 memory address. Once second stage is loaded, we need to call it by simple long jump. Let's not forget we need to set the last 2 bytes to AA55. Second stage. Bot to protected mode. Great, now we just got rid of our code limitation. We are no longer restricted to 512 bytes. However, we still have restriction in memory size that we can use. As I mentioned before, we are using real mode that use two-part segment offset addressing. To convert this into a linear address, we simply calculate segment times 16 plus offset. Both segment and offset are 2 bytes unsigned numbers. Our highest address is 64K segment and 64K offset, using the linear formula that allows us to address roughly around 1 MB of memory. This 1 MB includes a lot of restricted memory space like BIOS interrupt, screen memory mapping, our code. we do not have much memory available. Our game will run in resolution 1024 on 768 with 16 bits of color. This is around 1.5 MB just for screen. Technically we could do that in raw mode, because VESA by default use screen banks, so we have access to a screen window of a 64 KB at a time. To draw anything on a screen, you need to calculate both bank number and offset in bank. We will talk about this later. To unblock more memory, we need to switch to different mode. We will switch into protected mode that uses full 32-byte address to access memory. This way we will have easy access up to 4 GB of memory. However, there is a huge downside of switching to that mode. We no longer have access to BIOS interrupt, so forget about easy discrete, graphics switch, etc. In protect mode we are still using two-part addressing, segment offset to address memory. However, when we switch to protect mode, we also switch to 32-bit architecture. Furthermore, segment is no longer a direct part of an address, but it points to entry in GTT table that we have to define in order to switch to protect mode. From now we call it a selector. GTT table is just a simple array of memory descriptors. Each descriptor tells the CPU base where the segment begins in physical memory, limit how big it is, access flag code versus data privilege level present writable. This way you can define access right to different memory blocks. In a simple OS we use a flat memory model, so both code and data map whole memory. First descriptor in GTT table is always null. We have our GTT table, but CPU does not know yet where we hold this table. We need to define GDTR. GDTR is a simple structure that has only two fields, size of a GTT table and address to that table. We have defined GDTR, so now we need to tell CPU where is this GDTR located. We do it by a simple lgdt call. Important note, CLI disable interrupt. There are some interrupts like clock that will fire in a short time interval. We do not have access to them in protect mode, so we have to disable interrupts. If we don't do this, OS will crash. Finally, we enable the protect mode by setting bit 0 in CR0 register, and then we have to do the same far jump trick to switch segment register. So it will point to a sector entry in GDT table. Now you may think that you already have access to all 4 GB memory. However, by default, CPU has 820 gate disabled for backward compatibility. The 820 gate doesn't block access entirely, instead it forces the 21st address line to 0. With the 820 gate disabled, the address space wraps around the 1 MB mark. This was the hardware trick to emulate the old 8086 CPU behavior, which could only use 20 address lines. Only when we enable the 820 line, the processor can access memory address above the 1 MB limit correctly. There are many ways to enable 820 gate. I will use the fast gate method that just do a single write to a port 92. Switching to protect mode comes with a price. All the BIOS interrupt I was using for disk, graphic, keyboard, they only work in real mode. Once I'm in 32-bit protect mode, those service disappears. Instead of calling BIOS, I talk directly to ATA controller register. Issue a read command, wait for the driver to be ready, and pull the data into memory. This is where it starts to feel like you're really talking to the hardware yourself. Graphic. Game requires graphic. The easiest way to enable it is to use BIOS interrupt. We're just going to enable VESA before we jump into protect mode. This way we'll not have to do it later on by ourselves when the interrupts are not available. Switching is quite easy. We just call interrupt with specific graphic mode we want to use. Based on this list we need to enable 117 mode. You can see that there is a magic 4000 value added to mode. I mentioned before that VESA does not give access to whole screen buffer. Instead it splits screen into a banks, 64 KB blocks. When we want to write to a specific screen position, we need to calculate bank number and ask BIOS to switch current screen window. This requires to use interrupt and make whole drawing much slower. However, as you already know, we can't simply use BIOS interrupt in protect mode, so this is a problem. Fortunately, VESA has a linear frame buffer extension that we can enable. When we do it, we'll be able to get memory mapping for whole screen, no need to use banks. We simply enable it by setting 14-bit to A1. This is what 4000 hex is for. Once we do that, we will pull VESA info, and we fetch only important information. Bytes per scanline, X resolution, Y resolution, bits per pixel, and physical address. Physical address is important. This is where the screen memory is located. Anything we put there will be visible. We'll talk how to use it a bit later. Load C kernel. Writing whole Tetris in assembly would be a painful and long process. Let's not go this way. Instead, we will load Linux executable file. This way we will be able to start using C. Loading kernel will be as easy as loading second stage. We will do it before enabling protected mode. This way we can use the same code that we were using to load second stage. All we need to do is just specify different arguments. Once we set up everything, we can just jump to protect mode and set segment register to use data GDT. Next we search for elf file header to find the code entry point. Once we find the entry point, we can call it with arguments. This is our kernel entry point, a part of elf file that executes C main function. This is our kernel main function, which argument provided from assembly code. At this point we have set up protected mode, so we can use whole memory. We also enable VESA graphic, and we switch to C kernel. Lot of work behind. Memory management. If you ever create a program, you know how important it is to have access to heap memory. In C we use malloc and free function to do so. But these functions are provided by operating system, so we can't use them. We have two options. Because our application is operating system, it has whole memory for itself. So we could plan memory allocations and just use static memory address. Option 2, we can write our own allocation system. At first, I considered doing static allocations, but I quickly realized that this is very hard to do. Without dynamic allocations, you can't even do a simple function that returns new object. You can also forget about dynamic structures like list, tree, or maps. Well, technically you can plan memory upfront, but maintaining that will be a nightmare. Planning ahead is even harder when you think about allocations in loop, or just nested code that try to create new objects. Finding mistake will be insanely hard because we can't simply debug on emulator. Maintaining and further modification would be almost impossible. I decided to build a simple, dynamic, two-way link at least to store memory. I came up with this structure. I simply have a pointer to next and previous element, size of this block, and a flag. At the moment I'm using only a single flag to mark allocated blocks. I will keep this structure at the beginning of each memory block. At first there is a single record that defines whole memory space and mark it as free. Allocation is simple, just iterate over the list and try to find smallest free memory block that can fulfill memory request. We want to use the smallest possible block because we don't want to fragmentate our memory. Once we find the requested memory block, we just slice it and create new memory entry. Next we need to build free method. This method, however, can't just simply mark block as free. Imagine you run a loop that constantly tries to allocate and free memory. If you keep slicing memory, you will end up with a lot of small memory chunks. This can cause out of memory, not because there is no more free blocks, but you can't find big enough block you need. It is important to try to connect block into big chunks when we release memory. First, we mark block as free and we immediately add this to a total free memory. Next, we just try to relink memory. So we check previous memory chunk, and we also have to check the next memory chunk. If it is possible, we create single block and remove one header. Finally, we can initialize our memory like this. You may ask why there is a pointer type everywhere. This is because I have created the test application to debug and test allocations. On emulator, pointer will be 32 bits, however on my macOS, pointer are 64 bits. I can switch between these two types by just simply changing pointer accordingly to a system I try to run it on. This way I can easily test it on my macOS like this. Drawing. Let's have a look what type of data we have from VESA info. LFB. This is a linear address of our first pixel on a screen. We use 2D coordination system, top left pixel is 0, 0. We use x-axis for image column and y-axis for image row. Column number increase to the right and row number when we go down. Resolution X. This value tells us how many pixels columns do we have. Resolution Y. This value tells us how many pixels rows do we have. For our resolution, res X will be 1024 and y-axis will be 768. Bytes per scan line. This value tells us how many bytes are used for a single image row. If we use 16 bits per pixel, this means that for every pixel we need 2 bytes. For our game resolutions, this means we need 2048 bytes for each row. This value might be bigger than resolution X multiplied by bit per pixel, if resolution includes padding. Additional padding might be used for better memory alignment for each row. Finally, we have BPP, which is bit per pixel. This defines how many colors we can present on screen. Our Tetris will use 16 bits per pixel for red, green, and blue. This format uses 5 bits for red and blue, and the 6 bits for green. So how we draw specific pixel? Let's look on a simple example. This grid represents a small image that have dimension 10 on 8 with 16-bit color palette, and base is a pointer to a top left corner, so the 0, 0 point. How do we access ping pixel? First we need to define pixel chords. We count from 0, so the column number is 7 and the row index is 5. This means the chords are 7 and 5. Computer memory is really just a long one-dimensional line of addresses, like a giant row of boxes. But when we draw on a screen, we think of 2 dimensions, x and y. The green arrow represents memory alignment of each row. Row with index 1 is right after row 0. Row with index 2 is right after row 1. There might be a few bytes separating each row due to padding. To connect the two, we map each pixel xy position into the one-dimension line. The trick is simple. Rows of pixels are laid out one after another in memory. So to reach pixel at column x and row y, we skip over all the rows before it. In this example, 5 times resolution x. Then we need to move x steps into the current row. For this example, additional 7 pixels. Let's not forget that this is the relative offset, so we need to add base address. This is not fully correct formula. We need to take into account bit per pixels. In this example, we use 16-bit, which is 2 bytes. To skip single pixel, we need to move 2 bytes, not 1. You have to take that into account and multiply both column and row by 2. Now we can create generic formula. Base address plus pixel row times resolution x and times bytes per pixel plus pixel column times byte per pixel. This formula is valid only if there is no padding between rows. To include padding, we do a small modification. Instead of multiplying row by resolution x and by bytes per pixel, we multiply it by scanline size. We can now calculate address in memory for any pixel. Now we need to know what to put there. We can split that into 2 different approaches. With color palette when bit per pixel is equal or lower than 8 bits. Without color palette when bit per pixel is higher than 8 bits. If we are using 8 bits, we can only use 256 colors. In that case, we create a palette of 256 elements. Each palette element contains 3 values, red, green and blue. Every value that we set for a pixel will be used as index to our palette definition to decode actual color. When we use 16, 24 or 32 bits, we no longer need palette. For each pixel, we just set RGB value. 24 bits per pixel use 8 bits for each channel, red, green and blue. 32-bit either do not use 1 byte or use it as an alpha value, transparency. It is a bit trickier with 16-bit, we just pack red, green, blue into 2 bytes by scaling down values. One way to do it is to use 565 format. This means we use 5 bits for red, 6 bits for green, and 5 bits for blue. This can be done like this. These values from mask color shift can be fetched from VESA info block, or you can just hardcode them if we use specific mode. Now you know how to define image and set pixel color. Let's create structure to hold image. We define base address, buffer, and dimensions. We don't use padding, so this is enough. For simplicity, we also use 16-bit only. The cool part about this is that we can use the same structure to access our screen. All we need to do is set buffer to LBE pointer. Now I had to build few basic functions that can draw to this image structure. Let's have a look on a method that can put one image into a back buffer at specific position. We could make this more generic by replacing back buffer reference with additional input image. We just copy line by line into another buffer with dx and dy shift on specific axis. Once we are done with driving, we simply copy back buffer into a screen. There is a small trick. I cast 16-bit image into 32-byte array to copy 2 pixels at a time. I have built few more functions for driving lines, printing text, clearing buffer, etc. This, however, could be a separate video. Custom file system. I also need a way to load game assets, background, block, textures. This requires HDD access and custom file system. I did not want to overcomplicate it, so I came up with this very simple file system that looked more like a data file. It starts with this header. Header have only 2 numbers, offset in bytes where the file meta begins, and file count. File data offset should point right behind the file system header to file meta array. If we add more data to file header, this pointer will make it backward compatible. Starting at the file data offset, we find an array of file meta structures, each describing an individual file entry. File meta contain file name, location, and size on disk. I then create findFile method. This method returns file mapping in memory that can be used to read a file data. Because I'm lazy, I don't want to invest in full file system just to load few bitmaps. This is why when I initialize file system, I load whole file system into memory from HDD. I have single disk read as a startup and then just use memory mapping. I'm reading file system in protect mode, so I have to write AT-AT drivers for that. AT-AT driver is quite easy to write. All you need to do is write some data to port and wait. Now we need a way to create this file system with actual files. I wrote a simple program in C that I run on my PC that reads list.txt file from asset directory. This file contains a list of files that I want to pack into my file system. For example, background and block BMP. Then this tool reads this file list and fetch them from asset folder. It will then create this file structure for me. I just need to copy the structure into disk image file. Keyboard. Finally, I have created keyboard driver. Well, driver is a big word for that. All it does is read key scan code from ports 60 hex and decode them. Decoding is quite easy. Scan code contains key code, unique number describing key on keyboard, and bit telling us if the key was pressed or released. There is also scan code for extended keys. When we get this extension code, we know that the next key is special and requires a bit different mapping. On every game loop, we read key events and parse them like this. This sample pulls up to 16 key events. It checks if a key was pressed, and if yes, then it checks the key code. If user press left arrow, we try to move Tetris block left, but before doing it, we check if the position is valid. In addition, my keyboard driver will emit key again after a few hundred milliseconds if we keep pressing. When we press arrow down and hold, we will automatically repeat the key press. No need to fast click key, just hold. Put it all together. Finally, we have all building blocks, so it's time to build Tetris. We start by defining game block. This is 3-dimensional array. The first dimension defines Tetris block, like square or a line. Second dimension is selected rotation of the object. Each element can be rotated by 90 degrees, so we have 4 possible rotations. Last dimension is relative shift of each component. Each Tetris block consists of 4 squares, and each square can be shifted on both x and y axis. So we have total of 8 numbers per block definition. We create 2 methods to handle the blocks, getBlockDef and drawBlock. First one returns block definition based on type and rotation, so it simply returns the inner array of our block definition. drawBlock. This method will draw selected block type and rotation onto back buffer at x and y position and will use block's texture for each block component. This method will be used to draw next block and current moving block. Next, we define game field. This is the 2-dimensional array mapped into 1 dimension. 0 means the field is empty, and non-zero value means there is a block, and a value is an index inside block's textures. We need a method to clear the game board by setting every value to 0. This method will be used to initialize game field. We also need a draw method that converts this board map into textures on screen. Next, we create a method to validate block position. Cx and Cy is a block center position, and block definition is just inner array of block definitions. We just iterate over each array element and check if the position is valid. This will tell us if any block component interferes with anything on the screen. When the block tries to move down to invalid position, we have to stop it. Block cannot move anymore, so we fill the board with this block. There is one key thing missing. We have to clear full lines. If we don't do this, the user will never get single point and lose quickly. We just check every single line from top to bottom. For every line, we first assume that we can clear it by setting clear line to 1. And then we iterate over every column in that line. If any column in that line is empty, we reset clear flag. Once we finish checking every column in that line, we verify clear line flag. If it's set, then we remove that line by moving lines above by 1 line down. So technically we are squashing. We also count how many lines were removed to apply score, and calculate bonus for multiple lines. Finally, we need to initialize everything and start game loop. We start by initializing memory, graphic, file system, and we initially reset board. Next, we load image and generate block texture from block. Then we initialize keyboard and create current block, next block, and reset score to 0. Inside each game loop, we get the key press info and move block depend on the key pressed. We allow movement to valid position only. Finally, we draw everything like background, game board, block, and score. All drawing happens on back buffer, so we just have to copy it to the screen. Block automatically moves down when enough time passed. If after move we will end up in invalid position, we will put block, try to clean line, apply score, and then check if spawning new block will put us in invalid position. If new block end up in invalid position, the game is over, and we reset board, score, and skip frame count. Hope you guys like this deep dive into a bare metal Tetris. I'm thinking about where to take this OS next, so let me know your ideas in the comments. Don't forget to hit the thumbs up if you enjoyed the ride. See you next time.